Hello everyone. So far in the previous lecture we have discussed about how electromagnetic wave propagates in free space and lossless dielectric medium as well as lossy medium. So, when we discussed about lossy medium, we just additionally consider that sigma, that is conductivity, is not equal to 0. Some conductivity is there, and using that actually we could find out that the propagation constant could be modified as alpha plus j beta. It will have a real part and complex part, imaginary part. Real part is alpha, that contributes to loss as it propagates, and beta actually contributes, the imaginary part contributes to the phase, that is a phase constant as it propagates. So, that is what we have discussed in the previous lecture. So, now we will be discussing about electromagnetic waves or wave propagation, light wave propagation I mean to say, in metals and semiconductors. So, as you know, there is some distinction, some differences are there in metals and semiconductors. So, metals, you know that if we just think of a band diagram, suppose this is at any x axis is something position, and then y axis if you just consider energy of electrons inside the metal or material, then we know that there is a band always energy of electrons inside metals. It is like a band. So, from here to here, this is called band. Anywhere, any energy states, it can take electron, and you can have sometimes there is gap, so called band gap, and then you can have another band also. So, you can think of some other band. Okay. If you just think about this thing, so this is band gap, and then it can have another energy bands will be there. So, typically in in metals, particularly if you just consider metals, if you see the topmost band, all the energy lines, energy solutions, whatever you get within the band, they may not be occupied, and you can see that up to this point everywhere you can see anywhere electron is there. So, some kind of electron density you can consider n will be there, and that will be occupied up to some levels, and above that in this region, for example, slowly it will be reduced the density at higher energy state following so called Boltzmann distribution. Okay. So, you can think of that density, more density will be at the lower energy levels, and slowly it will be reduced at the higher energy level. So, density of states accordingly, and according to your so called Boltzmann distribution or Fermi-Dirac distribution, you can say, that will be distributed. So, in that case, normally any electric field if you apply, that can be electromagnetic wave, that can be some DC to certain fields, then electrons can actually energize and they can be easily movable, they can conduct current. That is why some metal you will see that the conductivity sigma, whatever I consider as sigma, that will be very large, that can be large basically. Okay. For metal. However, for semiconductors, if you see that the gap, there is a clear band is there, but sometimes what happens that the gap is a little bit, it is a small, not so large. If it is small, then what happens, the upper two bands, if you are just considering this one and this one, what happens? Some electrons from this is supposed to be completely filled, this band, some electrons it can go to the higher band where supposed to be empty at low temperature, but at room temperature electrons can go. So, you can see some kind of electrons here occupying at room temperature, and here some empty space will be, empty point will be there, some vacancy will be there. So, in that case normally this electrons energized from the room temperature, lattice vibration, etc. it can take. So, you can say some carrier electron is here, and here you know huge amount of energy bands, energy solutions will be there. So, electron can occupy and they can actually freely move. If they can little bit energize also, they can move. So, they can contribute here, electron will contribute in the, this is called conduction band. So, called I can write conduction band. Okay. This is conduction band and this can be called as a valence band. So, in semiconductor you know conduction band and valence band will be there, and this will be your so called bottom of the conduction band energy, and this can be called as a top of the valence band energy, and we call this Eg equal to Ec minus Ev. For example, in case of silicon, this Ec minus Ev equal to about 1.12 electron volt. Okay. So, that is the band gap. So, it will be silicon up to here you can see some kind of band that is called conduction valence band, and then there is a gap of up to 1.12 electron volt, then you can have a conduction band. So, some electrons can easily overcome this 1.12 electron volt at room temperature, and that they can occupy in the conduction band. So, that is why it can be somehow some carrier will be there in the conduction band, and some holes, so called holes, this will be called as a holes will be in their valence band. So, in that case both electron and hole can contribute. So, we can say for electron we can write N and for hole we can write sigma. So, we can have conductivity. Okay. However, this conductivity you can control also. If you, for example, if it is silicon, what happens? You can have some kind of dopant like pentavalent, silicon normally tetravalent atoms are there, crystalline structure. So, if you are just doping silicon with say for example, phosphorus pentavalent, then this fifth electronic states normally comes very close to conduction band, energy solutions comes very close to conduction band. Okay. So, in that case this energy separation from the bottom of the conduction band, it is very small. So, easily that electron can contribute to the conduction band, and you can get lot of electrons in the conduction band, free electrons. So, in this way this will be called as a N type semiconductor, and thus you can contribute conductivity in sigma N. And again if you doped atoms like boron, then you can get boron, you know this is a trivalent atoms. So, you can see when it is just bound inside the silicon crystal, that means occupying a sides of silicon, then the fourth electron, it is actually shortage in boron. Boron in valence electrons there are 3, normally silicon valence electrons are 4. So, that fourth electron which is not available in boron, that will occupy a state somewhere here just above the valence band. So, in that case some electrons can easily energize and occupy that energy, and it will be attached to boron. That is why negative ions will be, immobile negative ions will be created, and in return in the valence band you see empty space. So, some shortage of electrons. So, that is how we can say that those where electrons are not available, they are holes basically. So, in that case it will be called p type semiconductor, and you can also contribute conductivity in holes. So, that is how basically whether it is a metal or semiconductor, then they can be just approximately considered as a material with having some kind of sigma, which actually contributes to similar equivalent to your whatever we discussed earlier, dielectric lossy dielectrics. So, some sigma value you have to consider not equal to 0 you have to consider, and you have to treat your electromagnetic wave accordingly. So, there is a one third situation you can think of. Suppose the same thing you are not doped, silicon for example, if it is not doped at all, it is intrinsic and very little amount of electrons will be available in the conduction band and very little amount of holes will be available in the valence band. Okay. So, this sigma will be slightly lower, it is kind of not so high like conductor. Okay. So, it is not doped at all, whatever carrier you will see in the conduction band and valence band, that is because of the thermal excitations. So, in that case, if any electromagnetic wave propagates here, which electromagnetic wave if it is propagating through the material, this is a position I am saying that everywhere energy electrons will be occupying this band and conduction band, there will be free things will be there. So, if a electromagnetic wave is propagating as a light, for example, electromagnetic wave, light wave, if you know light wave, you can imagine quantum mechanically that is a stream of photons, and that stream of photons normally h nu, energy will be h nu equal to h nu, and sometimes you can call it h by 2 pi times 2 pi nu, and h by 2 pi we call it h cart, and 2 pi nu means angular frequency h cut omega. So, that is the energy of a photon. If this energy of a photon, you can calculate energy of a photon, if lambda equal to 1550 for example, 1550 nanometer, then this energy you can consider, basically this can be considered as hc by lambda. So, c and it is a Planck constant and lambda, then you can calculate the energy. If this photon energy h cut omega is less than Eg band gap, then that electromagnetic wave, it will be actually can propagate inside the semiconductor also if the photon energy less than band gap by the way, then it can propagate as if it is like a lossless dielectric medium. Okay. So, even though it is a semiconductor like silicon, germanium, gallium arsenide, if you are treating and if it is undoped at all, completely undoped, intrinsic material, and any electromagnetic wave, consider if you consider as a stream of photons and photon energy is just less than band gap energy, then that semiconductor, that particular semiconductor, it can be silicon, it can be gallium arsenide, it can be germanium, that can be considered as a just lossless dielectric medium. However, when it propagates, of course, what happens if h cut omega greater than Eg? It can happen because energy is higher, the electron in the valence band can absorb the photon energy and photon will be destroyed, and then that electron can go up. So, you can create one electron here and one hole here, one electron will be here and one hole will be in the valence band. So, electron hole pair will be generated. So, in that case you will see some kind of certain kind of absorption. So, one thing is the absorption. Absorption I will be talking because that absorption, and sometimes also what happens if certain condition is created, the electron can reoccupy the hole and can emit again photon. So, this type of absorption, emission can happen also, photon absorption, photon emission can happen, and that is normally quantum mechanical phenomena. We will be discussing that later, we will be discussing when we shall discuss about laser diode and photodiode. For the moment, we can consider that okay, semiconductor as a dielectric material for electromagnetic wave having energy, photon energy less than band gap, and in that case, you know that this can be considered as a dielectric though, but never you have to consider also there are some electrons because of the thermal excitation etc. will be there. That electron in the conduction band and some holes in the valence band, they can contribute some kind of conductivity. So, that conductivity you can consider it is not completely lossless dielectric, it is a kind of lossy dielectric material medium. Okay. So, with this understanding, that conductivity, band gap, transparencies, all those type of things if we consider, then we can think that electromagnetic wave when it is propagating inside the material, whether it is a metal and it is a semiconductor, how that behave. So, normally it is slightly different than what we have discussed when we consider lossy medium, that sigma is there. The reason being, both metals and semiconductor, metals you know that what do you call that, the conductivity can be very large, and semiconductor also if you dope or even room temperature, it has certain kind of conductivity. So, depending on the conductivity you can see that certain frequency range it may transmit, and sometimes you can see that the velocity of electromagnetic wave, phase velocity of the electromagnetic wave inside the material, whether it is metal and semiconductor, depending on the conductivity and so on, they will travel with different velocity, different frequency, different velocity. So, there will be some kind of material dispersion. All these we think we need to discuss, because we have to deal all this semiconductor as a dielectric material, semiconductor, dielectric material, metal, all these things you need for developing your photonic integrated circuit, especially when you talk about CMOS electronics and CMOS compatible photonics circuit, you need to deal all these materials. So, we need to know how they react, how they behave, all these material as a function of frequencies as far as light wave propagation is concerned. All right, let us move on. So, you know, if you want to discuss about so called light waves are electromagnetic waves governed by Maxwell's equation, that is I continuously am insisting, and you know these are the Maxwell's equations. I am just repeating here so that these equations you can always follow and refer following the discussions when I discuss different phenomena. So, now you see metals are in general, these are the property whatever we discussed so far, it is a non-magnetic material. So, here when I am just considering B equal to mu H equal to mu 0 mu R H magnetic field, this most of the time whatever metal we use they are non-magnetic, that is why mu R should be equal to 1. You can directly you can use that. And conductivity, which I consider that is a very high, but that conductivity you can have an expression. What is that? That is N is the density of electron, free electron I mean to say, and E is the electronic charge, and tau is the tau is a very important thing. This is basically called relaxation time, or whenever you apply electric field, sometimes what happens, even though you are not applying electric field, the electrons in the metal, they are like a free, they are just like a Brownian motion, and they will be when they are just randomly moving around, they can actually somehow sometimes it can scatter out of the lattice points, and that is the collision, they can collide with the lattice points. So, in that case it will suddenly it will stop its motion, and then again it will start taking up the energy. So, that type of situation in time taken between two collision is called relaxation time, tau. Typically that is 10 to the minus 14 second in case of metal where density is very high. And AME of course we can say that mass, electronic mass, and if it is free, completely free, it is 9.1 10 to the minus 31 kg, and sometimes you can modify this mass because of the inside material medium we have little bit potential, so called periodic potential will modify the mass, that will be called effective mass. In that case effective mass can be higher than this or can be lower than that depending on the dispersion relation inside. I am not going into that right now. Okay. So, now you know we can find the conductivity, if you know the density of electrons and also the relaxation time. There are various experimental techniques you can find that you can use them to find out the conductivity. Here I have just given one table directly taken from textbook, where we see that aluminum, copper, gold and silver, these are the material normally used, typically used in any electronics, CMOS electronics, particularly aluminum and copper is very popular. They are frequently used in CMOS industry. If you see the free carrier concentration, free electron concentration, it is in the order of 18 into 10 to the 22 per centimeter cube. It is very large. And copper is slightly lower. However, if you see conductivity, you measure or calculate depending on the effective mass as well as tau value, you see copper conductivity is higher, relatively higher. This is actually 3.5 into 10 to the power 5, it is a per ohm per centimeter. Per ohm means sometimes it is called mho or sometimes it is called Siemens per centimeter and so on. Different unit you can use, but typically in SI units we can just write like this. Okay. So, these are the conductivity, and this is much higher than it is than 0, right, 10 to the 5. In case of dielectric where no free electrons are there, this is completely 0. So, you can imagine this can contribute lot of losses inside the material medium, just simply you can conclude. And if you are just considering silicon, normally in silicon you can go doping concentration in the order of 10 to the power 19 to 10 to the power 20 per centimeter cube, 20. Normally in a crystal, silicon crystal, the atomic density is in the order of 10 to the power 22. So, you can replace maybe every 100 silicon atoms, one boron on phosphorus you can replace, still you can maintain a silicon crystalline structure, and then once you dope you can get this type of concentration. So, this type of concentration also you can put and you can try to find out the so called conductivity. Typically in case of semiconductor conductivity you are writing like this, N E mu, so called mobility. What is that mobility? Mobility actually expressed by this one. So, you know drift velocity of electron inside crystal, it is proportional to electric field you apply. Okay? Because if you apply electric field, electron will start moving, and that is called that is somehow called drift velocity, and that will be typically it is proportional, but this proportional constant we write as a mobility. Okay? Electric field and drift velocity. Okay? So, once you know the mobility, then you can write any mu. Normally this mu stands for E tau by m. That is what you are getting, sigma equal to n E square tau by m. Okay. So, in case of semiconductor and metal, you can treat alike as long as you are considering the carrier concentration, doped semiconductor or some intrinsic, and also metals with high concentrations, electron, free electrons, etc. You can treat it alike. Okay. So, now one important conclusion here, we will just try to show that in case of metal or semiconductor, we know that any electromagnetic wave propagation inside the material medium, we need to know 3 parameters, sigma, epsilon and mu. In case of semiconductor or conductor, we know that this is nothing but mu 0, mu are equal to 1. And normally this we consider epsilon or epsilon 0, and sigma, that is what under consideration, right. We will show that when electromagnetic wave propagates, particularly at higher frequencies, optical frequencies, that time the sigma and epsilon r, they are somehow, their property is somewhat blurred. You can actually relate sigma with epsilon r. Depending on the sigma, you can actually estimate what is the epsilon r value. Actually, frankly speaking, electromagnetic wave propagation in metals or semiconductors, heavily doped semiconductors, whatever you can consider doped semiconductor, they can be explained by either of epsilon or sigma. That is what the conclusion we will see. Fantastic. So, let us move on. We will little bit modify towards that point, because you know in a semiconductor and metal, you are talking about a lot of free electrons. So, that free electrons, when it moves, it is not completely free, of course, from the metal or semiconductor, metal or conductor, because electrons in that case, if it is completely free, it will come outside the metal. It is somehow bonded. So, we actually, when we are talking about the Maxwell's equation, particularly Gauss equation here, there we actually decompose the charge basically. So, divergence D equal to charge density, that we consider as a two part. One is called charge external, and charge external you can think of something, it is a free or something incoming excess carrier related to that, and rho internal, that is related to somehow it is part that is bonded to lattice points or somewhat internal polarization you can think of. Okay. So, we can call it external charge, internal charge. And similarly, particularly rho v we are considering in a dielectric or free space, that some charge is there. In that case we can consider rho external or whatever things comes, and internal, that is the internal charge will be, instead of rho v we are just decomposing into two parts. And similarly, if we see this equation, you have a current density which is actually so called sigma times E, that is actually the conduction current, and that is how you are getting the current density. That current density also you can think of about some kind of external current density as well as internal current density. Typically JC we can just think of J external, and we are just adding internal. So, we are just trying to see semiconductor and conductor, this is a two part of charge density can happen when electromagnetic wave is propagating. One is external and another is internal. Okay. So, then this displacement vector, what we are showing here, expression we have discussed earlier. From there, if we just little bit move on, just we know that divergence D equal to divergence if we just try to write, then divergence of this part also. So, if you just put down that thing, then you can say divergence, both divergence D, you are writing divergence D plus equal to divergence of E epsilon 0 plus divergence of P, that is both sides if you are taking divergence. And if you are just considering this rho total charge, then we can say that this divergence E, basically epsilon 0 E, that actually gives you the total charge. So, this will be like this, divergence E equal to, if you are writing, that is total charge, then divergence equal to rho total by epsilon 0. So, if you are just writing this one, this total charge with the electric field and epsilon 0, whatever the things are coming, that is actually total charge. This total charge actually contribution coming from your internal and external, that is what the understanding, modeling. Okay. So, if you are just putting this one here like this, then obviously divergence P, that means the polarization density and its divergence, if you are taking, that is nothing but minus rho internal. So, rho internal, whatever we are trying to define, that internal charge, that is because of the polarization density. Polarization density means you are just applying electric field, then you have a electron will be little bit displaced with respect to the atom, and then you can create a dipole moment per unit volume, that is actually called polarization. That polarization happens because of the charge separation, right. So, if you are taking divergence of P at any point, if you are just talking divergence P, whatever the polarization you have, you are just taking divergence, then you can just consider that is nothing but the charge. internal charge and negative charge. That is how you can just incorporate rho external, rho internal. So, because of the polarization density, you are having additional charge. That is how must be added to the external charge. That is the whole idea. Fine. Now if you are just considering continuity equation, charge conservation, charge current density, anywhere current density, that means divergence of J, how much current is diverging out. If you are at any point, if you are trying to find at that particular point, suppose all the current density, if you are just putting divergence at any point, then what you can see that particular point, what is the charge rate of change of charge density. So, rate of change of charge density, that must be negative, that should be reduced, that is why you see the current diverging out. So, we write divergence J equal to del rho minus del rho del T, that is how we call it as a charge conservation. Okay. So, if you are just again know that rho equal to rho external, current equal to divergence J equal to J external and internal, in that case if I write this one for internal case, then I can say that del rho internal by del T. Whenever I am taking internal current density, I have to write internal charge. So, that means this internal charge variations, okay, we can say that we have already discussed earlier here rho internal is a divergence P. So, if I just put here divergence P del rho del T, so I can write that divergence, I can take it out. So, this one I am writing del T times divergence of P and minus sign will be there, right. So, what I can say, this one I can take it outside, and because it is a space dependent, del equal to del x, del y, del z, 3 different direction, and del T I have taken. So, this one I can write here. So, comparing these two, I can easily write that J internal equal to del P del T. So, internal current density, we can say that it is a polarization, rate of change of polarization density. Rate of change of polarization density we can define as a internal current density. Okay, fine. Let us see, let us move on. So, I have just written down all these things, concept. So, what is the internal current density and divergence P equal to this one. This may be useful for further discussion, that is why I have just written this side, and let us see. This is a conclusion. This is a very interesting point. You see, since optical response in metals, of course, doped semiconductor should be also considered. It is a doped semiconductor is like a metal, because concentration can go up to 10 to the 19, 20, so on. Strongly depends on frequency. We need to consider non-locality response in terms of space and time by generalizing linear relationships. So, you understand that your electromagnetic wave or electric field, it is oscillating, electric field associated to electromagnetic wave, it is oscillating, and if it oscillates very fast, then what happens? Some effect in a material medium, that polarization density, which is the result of electric field oscillation, right, that can be that you cannot consider very local phenomena, because something your electric field is oscillating here, but material will respond, it will take little more time. And as the electromagnetic wave propagates inside the material medium, so you can think about that something happening in surrounding region, that also will affect polarization density elsewhere. So, that is why we redefine, we have to consider whenever we are talking about very high frequency optical frequencies, then this dense displacement vector, we have to consider this thing. This is epsilon multiplied by E, epsilon 0, epsilon r is the epsilon. So, that is what this one, we consider this one, yeah, epsilon, that is epsilon 0, epsilon r. But what we have to do, we have to integrate. Suppose I want to find out displacement vector at position or at instant time t, then I have to consider all other position vectors. These are some vectors r prime, r minus r prime, and you have to consider also r prime, t prime. Every other points, what is the electric field, that also contributes to the dielectric constant and r. So, this is r prime and t prime is the variable, I am just integrating. All position electric field I am integrating, and that how you are getting here, you have to convolution, you have to take convolution, then you can get the displacement vector. Similarly, for current density we know sigma E, sigma times E, E is the everywhere, you are varying r dr dt, and you are trying to find out what is the value at r and t conductivity. So, this in principle you have to take this one for your consideration of displacement vector and current density. Here we are considering internal current density as we discussed earlier. And then you see, by taking Fourier transform with respect to plane waves, you know plane waves we normally consider e to the power j omega t minus k dot r, that is a plane wave. You can write E0 and you can have some polarization and so on. This is forward propagating plane wave, and you can also write forward propagating plane wave like this, e to the power j k dot r minus omega t. Okay. So, this can be a plane wave because forward propagating, because sign I have changed only, okay, minus sign I have just multiplied. So, that also will be considered as a forward propagating. Earlier we have discussed this. Okay. So, what we have to do, if we just take a Fourier transform of this, then position and time, two variable Fourier transform, if we are just considering position is a real space, that will actually convert it into k space. Okay. That means k, you know, normally you know k equal to 2 pi by lambda, lambda is the reciprocal space, lambda length real space, and time will convert into frequency. So, in Fourier domain the convolution is nothing but just simple multiplication. So, epsilon 0 epsilon r, you just take a Fourier transform of this one, and that will be k omega, and so r will be converted into k omega and E will be k omega. So, just multiplication, it is just a simple principle of convolution and Fourier transform. Similarly, internal current density you can write like this. So, in frequency domain or Fourier domain, we are Fourier, this is actually whatever we consider in time domain, considering null localization. Okay. And here we are considering just Fourier domain, that if we know that what is the dielectric constant as a function of frequency and wave vector, and electric field as a function of k and wave vector, then we can just write like this, it's straightforward. Okay. Now, let us try little differently. You take this one and take time derivative, partial derivative, because d can be space dependent as well as time dependent, we just take a partial derivative. So, both side partial derivative, then it will be del p by del t, and del p by del t we know that is nothing but the current density, internal current density. So, we write down here, okay. And then del t we know that for a plane wave e to the power j omega t, it varies like j omega t. So, del t j omega we have used earlier also, and if we use that one, then what I write, del t j omega epsilon 0 epsilon r k omega e k w. So, d value we have already explained here, this one, and j also we already defined like this in Fourier domain. So, del t I have written j omega, epsilon 0 I have written epsilon 0 as it is, and then del t j omega and E equal to E k omega, E of k omega, and then j internal equal to sigma of k omega and E of k omega, sigma E. Okay. So, that is how we can define, and with a little modification, you just E cancel here, right. Then you can j omega cancel, you can just write j omega here, epsilon 0 you cancel, you can write epsilon 0 here. So, you get a nice expression like this. So, this is the thing I was just trying to explain in the beginning, that fundamental relationship between dielectric constant and conductivity. If you know the conductivity, then you can know the dielectric constant. at a particular frequency. By the way, this conductivity can be also, you can think of sigma 1 j sigma 2. If it is real part and complex part, then you can also consider this epsilon r can be represented here. So, that means you can either you need to know what is the value of sigma, or you need to know what is the value of epsilon r. So, either of them is useful to explain the polarization, internal polarization and electromagnetic wave, whatever the dispersion relations, that is I am going to discuss little while later. Hopefully, it is going good. So, now I have written down that expression, whatever the sigma and dielectric constant, their relationship. You know, spatially local response corresponding to k equal to 0. What is k? K, we know that k equal to 2 pi by lambda. So, lambda, if it is very large, then k value will tends to be 0, or at very long wavelength regime, that is what I meant. Then particularly that lambda, if you are considering with respect to the lattice point, whatever the electron motions etc., you are considering that lambda, if it is much larger than that spacings, it can be considered as a homogeneous medium as if. So, in that case we can say that epsilon k equal to 0, k equal to 0 means I am writing 0 omega, simply we can write epsilon r omega. So, for long wavelength means, you know, long wavelength means frequency is shorter frequency range. So, you can simply write that. So, at very low frequency, epsilon r is usually used for the description of the response of bound charges to a driving field, leading to an electrical polarization, while sigma describes the contribution for free charges to the current flow. That is the low frequency when it is happening. So, we can consider this one, you can just distinguish that E r omega, that is actually like a result of your polarization, dipole moment etc. is created, that contribution, but the conductivity part you can just distinctly you can consider there, that actually contributes to your current can flow. But at optical frequencies, when omega is very high, the distinction between bound and free charges is blurred. You cannot distinguish, because this polarization actually because of the bound states, and free electrons that will be contributing to the conduction. So, earlier for low frequency they can respond separately, conduction current as well as your polarization etc. you can think, but for high frequency this thing will be, you cannot really distinguish their difference. I will discuss that, that is going to be discussed. For high doped semiconductor, highly doped semiconductor, that is again and again I am saying that is like a metal, the response of the bound valence electron could be lumped into static dielectric constant delta epsilon r. Whatever the bound electrons are there in semiconductor, you know, there will be free carrier and then bound electrons will be there also. They can also consider, they can actually result into certain kind of dielectric constant. Okay. So, that thing if you are considering delta epsilon r and the response of the conduction electron sigma dash resulting into what you are getting, you are saying epsilon r, this is a lumped one. So, instead of 1 we are just adding delta epsilon r, that is actually for the bound electrons, and whatever the sigma it is there we have written. Or you can say that delta epsilon, you do not need to put that bound state, little bit modification, that you can put as it is 1 earlier, whatever it is written here 1 we can write, but this sigma prime, that conductivity, that can be modified like this. If you can modify this one and then if you just put here sigma value, then it will be giving you same results. So, in that case you do not need to consider what is the additional epsilon r because of the bound states or not, only thing you have to consider your conductivity is changed, that is it. So, that is the whole idea, some textbook they consider something like this. Okay. Now, so metals I just proceed little further, it is a very interesting part. So, I am just considering that okay, whatever sigma or epsilon r whatever you are getting this is the expression. You can just say that it must be because j is there. So, it has a real part, imaginary part clearly is there. So, I can say that sigma can be sigma prime, that can be considered like a real part, imaginary part. That real part will be again adding here. So, you can have real part and imaginary part, that is what. And then next level, I know that refractive index is square root of epsilon r, that is what we discussed earlier. Then we can say that here in this particular case, because it is a complex, we say that complex refractive index can have a real part of the refractive index and the imaginary part of refractive index. This imaginary part of refractive index, sometimes it is called extinction coefficient. We will discuss that a little later, this kappa, that is a special name, extinction coefficient. Okay. And then if you see that this two, if you just compare, you know that square root of this one, that means you are getting this one square root, if you are getting this one. So, you need to square root this one. So, normally in complex numbers, you know that how to find out what is the square root. If you are taking real part and imaginary part, you can find out epsilon 1, you can have n square minus kappa square, epsilon 2 is 2 n k. Just you square it, then you just equate it. If you just square it, it will be n square minus kappa square plus j 2 n kappa. So, if you square, that is a dielectric constant, that this means epsilon 1 and this means epsilon 2. So, that is epsilon 1, epsilon 2 you are writing here. Okay. So, what happens after that, if you just compare these two equations, you can try to find out only this one. I think this one actually sufficient, you know, n square minus k square epsilon 2 equal to 2 n k. You can try to find out what is the value of n. So, n can be written simply, just little bit of algebraic step. You can find out n1, n equal to this one in terms of epsilon 1, epsilon 2. If you know the imaginary part and real part of your dielectric constant, then you can find what is the imaginary real part of your complex refractive index and what is the, once you know that, you can find out kappa equal to epsilon 2 by 2 n. So, that is 2 n, whatever the n value it is there, you put down here, then both n and k kappa, they are actually can be derived once you know epsilon 1 and epsilon 2. Refractive index can be found out. This is a standard equation, you should keep in. Just from here you can just simple few steps and you can get that one. Okay. Now, recall Beer's plane wave propagating along z direction. Okay. I am just trying to explain that Beer's law. Earlier we have, you remember that we have just discussed we have discussed Iz equal to I naught e to the power minus alpha z, that is the Beer's law. I try to see how it can be expressed by considering sigma and this complex refractive index blah blah blah. Okay. So, this is a plane wave and this k, you instead of normally 2 pi by lambda, I have to write n tilde because you have a complex refractive index. Plane wave, when it is propagating inside the metal or semiconductor, I have to write 2 pi by lambda n tilde. Okay. So, now if I just simply write there, this can be modified as ax e naught j omega t beta z, where and e to the power minus alpha z, where beta equal to 2 pi by lambda n, this n, and alpha, because it is a imaginary part, multiplied by j, you can have 2 pi by lambda kappa. You know beta equal to basically 2 pi by lambda n tilde, 2 pi by lambda n we are considering beta here and alpha we are writing here. Then I can just simply straightforward we can get. It is not so difficult thing, no rocket science here, just straightforward. Fine. Now, we have also discussed the average energy flow, Poynting theorem, Poynting vector E cross H, and we know that electric field and magnetic field can be orthogonal to each other. If you just consider that thing, then we do know that energy flow is this one, E cross H, then it will be that I have borrowed the equation from earlier discussion, 1 by 2 eta E naught square e to the minus 2 alpha z. And then what we get? You see this one you can consider as I naught, and 2 alpha you can consider as alpha naught, and then we can consider intensity as it propagates, the power or intensity. Intensity is just power flow per unit area, that is it. Intensity we just consider I z equal to I naught e to the power minus alpha naught z. That is actually your so called Beer's law, where this alpha naught is the attenuation coefficient, attenuation constant for the intensity or power, and normal this alpha is the amplitude attenuation coefficient. Okay. So, 4 pi by lambda kappa. This 4 pi by lambda sometimes you can consider 2 pi by lambda 2 times kappa, right. So, you can write 2 pi by lambda c, you can consider c, you can consider 2 pi c by lambda equal to omega by c into kappa. So, sometimes it can be alpha naught can be written as 2 times omega by c kappa, and alpha will be so called omega by c kappa. So, intensity and amplitude they are just 2 times. Fine. Okay. So, one thing is this should be n square. I think this here you should see that n square expression should be corrected. Okay. N square and kappa will be this one. Fine. Now, regimes of transverse and longitudinal waves. So, transverse and longitudinal waves, you know epsilon r I have written like complex real part, imaginary part. Conductivity you can also consider, any one of them you can use, that is fine. And then next consider the wave equation. You take wave equation this one, curl of both side, then you can write mu 0 del t curl of h. Now, you know plane wave case nabla operator, that is a del operator, it is nothing but minus j k. So, you are just considering E 0 e to the power j omega t minus k dot r. K dot r if you are considering the plane wave, then nabla will be equal to minus j k and del t equal to j omega in this case, particular case. If you just consider that, then what you get? You get like this, and then this one will be vector identity, and right side instead of curl of h you can say this one, and sigma, instead of sigma I will be just writing epsilon r, that is why I am just writing this thing, one of them I am writing, because I do not need to write sigma additionally. And then substituting this two, this one will be k minus j k you have to write, minus j k you have to write, and k square. So, if you just substitute there of this operator, then you get left hand side this one, and right hand side you will be getting this one. You are taking mu 0 epsilon 0 equal to 1 over c square, and del t del 2 will be there. This will be actually mu 0 epsilon r del 2 e by del t 2, and del t this will be equal to minus omega square. So, if you just substitute there, then you get this equation. So, next thing what you get? Okay, the wave equation, transverse wave electromagnetic wave propagation. If you just considering transverse wave, that means you know k and e propagation direction, wave vector is perpendicular to the e, that means this will become 0. So, in that case, if this is become 0, that k square equal to, this k square equal to omega square by c square epsilon r. Okay, here it should be epsilon r, some type of error. Okay. Now, longitudinal waves. What is that longitudinal waves? So, we know electromagnetic wave is a so called transverse wave, but this is a special case when you can get a solution also. For example, you consider the propagation vector and electric field is parallel. This type of solution can be considered also. That type of situation mathematically you can consider. This one can be, suppose k is parallel to e in some situation. What happens? If this is the left, this one will become k square, because that will not be 0, no more 0. So, that means k square e minus k square e, that is the left hand side, right. So, this one and this one if you subtract, that will be 0. So, 0 left hand side and right hand side will be epsilon r. So, looks like a little bit odd that 0 and epsilon r. So, that means you can have epsilon r must be equal to 0. So, in case of you are considering longitudinal waves, that means your electric field is oscillating also in the propagation direction. That time also you can think of certain solutions which are called, which has to be, this dielectric constant has to be 0. If you get a dielectric function such that in certain points, certain omega points, k points, the value is 0, that means that particular point will result into a longitudinal wave. So, that is why we conclude that this is signifying that longitudinal collective oscillations can only occur at frequencies corresponding to zeros of epsilon omega. Interesting. Those collective oscillations occurs, that means we are talking about conductivity, electrons in motions, everything is there. So, if I have a electromagnetic waves and that electromagnetic wave has some frequency point where you get certain dielectric function and certain omega, you are getting 0. For that particular frequency, what will happen? You can see longitudinal wave. Normally, collectively entire electron cloud, okay, you can assume that that will be propagating, and that is how actually new type of subjects, topics came out. That is also sometimes used in integrated photonics, that is called plasmonics basically. We will discuss that if time permits. Okay. So, this is all what we could discuss about the electromagnetic wave propagation inside metal or semiconductor, okay, and then what could be the transverse electromagnetic wave and what would be the their dispersion equation. This will be called as a dispersion equation because you know k wave vector how it is related, but there is a chance that if it is metal and semiconductor, the longitudinal waves also can exist if the dielectric function has some solutions 0 at some frequencies.